Alright, cool. Let's get started. Thanks everyone for coming. I think we've had a bit of a late turnout today, but it's mid-sem, so I appreciate that you guys are all still here. Today we're going to be talking about surgical robotics. Can I just get you guys all to register your attendance, just so we can kind of keep track of who's coming, how people are coming. Just to get an idea, has anyone not been to any of the previous workshops? If this is the first workshop? Okay. Everyone else has been to? Oh, you haven't been to any other? Okay, cool. Sounds good. So I gave this build at the start of the other ones as well, but the goals of these workshops is essentially to give a technical overview of the current state of the art of various medical technologies, as well as going to what the future looks like as well with emerging innovations. And hopefully through that we can get you guys interested in MedTech. Now there's going to be some questions, some discussions throughout, which is why I kind of want you guys to sit closer to each other so you can discuss it later. So there'll be questions from me to you guys, but also if you have anything that you want to clarify throughout, please just stop me, put your hand up and just ask, like any time throughout, don't wait till the end. Most of you guys said this anyway, but yeah, my name's Ethan, I'm a final year medical student. Did my BMed Science last year in cardiovascular engineering. I'm interested in engineering, specifically hardware, design, manufacturing, and physical AI. And I'm a researcher / TA at the Monash Medical Technology Lab. All right, so today we're going to be talking about robotics, and more specifically surgical robotics. But because the idea is to give you some technical overview, we're going to start with a bit more of the engineering behind robots, and then in the second half we'll talk a bit more about what surgical robots exist, and then what the future of surgical robots look like, and we'll take a bit of a deep dive on kind of the most common one that we see, which is the Vinci Surgical System. So I guess first of all, what we want to think about is what actually is considered a robot. And before we get into the definition, what robots have you guys heard of or come across in your day-to-day life? Or at least know of, even if you haven't seen one in person. Just feel free to shout out.
Those in the restaurant.
Say again?
Those like in the restaurant.
In the restaurants, yeah, for sure. The service robots. Anyone else seen anything? The vacuums, yeah. You guys haven't seen any robots whatsoever?
Those robot dogs.
Robot dogs, yeah. The Boston Dynamics dogs, exactly, yeah. Nice. Anything, guys? That's all right. Okay. So there's so many different types of robots, and some of them are like the industrial robots you'll see in like assembly lines for manufacturing, especially like cars, for example. You see they have big robots that are doing a lot of that work. There are humanoid robots that is kind of the craze at the moment, and they're trying to integrate AI into that as well. There are service robots, which CJ mentioned, cobots. So those are collaborative robots. So they're quite similar in how they look to industrial robots, but they're designed to work with a human rather than to work completely autonomously. And then another example is autonomous vehicles as well. And there's so many more other types as well that I haven't gone into there. So then what actually defines a robot? So a robot is a machine that can interact with the physical environment to do three things. To first sense, to compute, and then finally act in this physical environment. And usually it's with a degree of autonomy. And there is a bit of ambiguity into that definition, especially about the autonomy part, but generally should be able to at least do those three things in the physical world. And so when you put them all together, you get what we call a closed loop feedback. And so, we get some sort of input from the environment that gets sensed, gets sent through a controller, which then makes some sort of decision, sends that signal to an actuator, so it's deciding what needs to get done, and the actuator will actually do whatever it is in the physical world. That will end up affecting the surrounding environment, and then it'll continually go through that loop. You can also get an open loop as well, but this is generally for more simple, repeatable tasks. Because if you think about an open loop, essentially you're just cutting this, so it doesn't get any feedback for what it does. So that's for simple tasks that you can program a robot, for example, to pick up an object and place it somewhere, and it's always just doing the same thing. So, if it slips like along the way, then it's not going to know where it is because the robot isn't now aware of where it is because it's not sensing. So you generally use open loop for more simple tasks, while closed loop would be used for more complicated tasks. And so the example I wanted to go through was the Roomba. So as Quay mentioned, that is a vacuum robot that some of you might even have in your homes. So the sensors that a Roomba has can be broken up into these three. So there's the bump sensors, so the bump is around the front. So when the Roomba hits an object, it will realize that it's hit something and it will turn. It has infrared and photocell sensors as well that detect obstacles and cliffs. So obstacles in front of it, but it also has sensors underneath, the infrared sensors pointing downwards. So if it gets to, for example, the top of a staircase, it knows there's nothing there and it will stop. And then in the middle, there's a microcontroller doing all the processing. And finally, there's a few DC motors that are working in the Roomba. So there's one for each of the wheels, and then one for the brush, and one for the vacuum as well. So the brush's job is to dislodge the dust, and then the vacuum actually sucks it all in. So when we put any set of these together, can we see any feedback loops looking at these sensors and actuators? Can we just give me an example of one, of how one might work? So let's take, for example, we start with a piezoelectric sensor. So it detects dirt, then what? Yep, and then what would the microcontroller want to do? Yep, so remove the dust? Yeah, exactly. So it'll tell the DC motors to turn on, to then start the brush, which will dislodge the dust, and the vacuum to turn on, to then turn that on. So yeah, so we start with the dirt sensor, goes to the microcontroller, the brushes will be activated, and then it will keep doing that until it's no longer sensing any dirt, and then it'll turn off the vacuum. And the same thing can be said for the other three. So if, for example, it hits an object, then it's going to know that it needs to turn, so it'll turn and it'll keep going, and then the bump sensor will essentially just turn off as soon as it's facing in another direction until it bumps into something again, and then it will be once again told to turn into a different direction. So then going a bit into the engineering, so one interesting thing is the degrees of freedom. So this is talking about the number of independent parameters that can fully define a configuration of either a moving part or a robot. And so these can be translational or rotational. So with a really simple example, right? So when we're thinking about degrees of freedom, we're thinking about in what ways, for example, a robot arm can move, but if we simplify it down, for example, let's take this tram, right? So in what directions can the tram move? Along how many axes can it either move translationally or can it rotate around when you're looking at this? So which way can the tram move? Straight forward or backwards, right? So it's along the one axis. Can it rotate in any direction? No, right? Yeah, so the tram doesn't rotate on its own. It would only be along the tracks, and the tracks, again, it's still going in that one axis. So there's only one degree of freedom for the tram. What if we take a 3D printer instead? So the 3D printer, essentially, this is able to move, and, well, let's keep it simple. Let's just say that the printer nozzle can move in a few different directions. So in what directions do you reckon it can move? 3, exactly, yeah. So in this example, the 3D printer nozzle can move up and down, left and right, and it's actually the bed that moves in and out of the page. But there are also 3D printers where the nozzle is able to do that movement instead. What about in a drone? And now we want to start thinking about rotation as well, because the previous ones were only translation. Any ideas? So how many translational degrees of freedom does it have? Yeah, it has the 3. Now what about rotating? In what axes can it rotate? Yeah, so if this is our drone, right? The drone can either rotate in this direction, it can rotate in this direction, but it can also rotate in this direction as well, right? So it's actually got 6 degrees of freedom. Basically 3 axes along which it can move, and it can rotate around those 3 as well. So you get 6 in total. So for any free body, any one individual body, it can have a maximum of 6 degrees of freedom. That's when you don't have any joints involved. Now, if we do include some joints, for example, the human arm, right? Let's think about how many degrees of freedom this might have. And so think through each of the 3 joints. So your shoulder joint, for example, how many degrees of freedom might that have? And so now they're not really translating, they're all rotating. Two? Good guess. So the shoulder can do 3. And if you think about it, it's more in terms of like it rotates in this direction, but it can also rotate on the spot as well. So you get 3 degrees there. What about in the elbow? So don't think about too much of like how the wrist is moving, just the elbow itself. So yeah, just 1, exactly. And then finally, the wrist/hand, it's a little bit trickier. But think of it as being pretty similar to the shoulder. So I would say really there's, it can rotate that way, it can rotate that way, but you can also rotate that way as well. So your arm is designed to have 7 degrees of freedom. And that's 3 at the shoulder, 1 at the elbow, because that's like a hinge joint, and 3 down here. And so you can see that ball and socket joint tends to have, it will have 3 degrees of freedom. And that's something that we'll have to think about when we think about robots later. Okay, so when we break down rigid robots, so there is soft robotics as well, but we're talking more about the rigid type. They're made up of 2 things, so links and joints. The links are essentially the solid sections in between all of the joints. So the equivalent in a human would be like your humerus and your radius and ulnar joints, bones, and then the joints in between are the same as in a human. And so you'd have the same in a robot. And so some of the common joint types that we see in robots, we already know about this one. So they call it spherical, but it's basically a ball and socket. Universal joint. So a universal joint is able to rotate 1 in this direction and 1 in up and down. Cylindrical can move up and down and rotate like a hinge, similar to this one, which is like a hinge as well. And prismatic, it can move in and out. And the helical one's quite interesting in that it's not that it rotates in this direction, it's actually that when you turn the screw, it causes this other side, the top side, to move up and down depending on how you turn the screw. And so you can imagine these only have 1 degree of freedom, while those ones have 2, and the spherical has 3. And so when you put this all together, you get robot kinematics. And so this is the study of how the joints affect the end effector or the other way around. So this is essentially a set of calculations that you design a microcontroller to be able to do. So in forward kinematics, you give it a set of joint angles, and the point is for it to be able to work out where the effector will end up. While if you talk about inverse kinematics, it's more about, okay, well, I want to get this to a certain position. Where do I have to how do I have to position all of these joints so I can leave the tip in that particular position? And so it's really just doing a bunch of maths in its own head as it's going through. And so it needs to be able to sense where all these joints are and work out where the end effector will be. Okay, so thinking through some of the robots we've already mentioned, or other things that we haven't mentioned so far, what sensors might need what sensors, that should be ORS, might a robot need? What does a robot need to be able to sense in the real world? And you can start really simply, what do humans sense? And then what can humans not sense, but there are sensors that can do other stuff too.
It depends on what the robot is for.
Yeah, so I'm talking just generally, any robot. Vibration, yeah, for sure. Sight, exactly, yeah. Anything else? Temperature, good. Where the joints are, very good, yeah. Anything else? So, sound, exactly, yeah. So audio and video input. Okay, good. So we can break it up into two types. There's proprioceptive sensors, which is very similar to what we think about in humans. So that's not just which way the joints are positioned, but just anything that measures the internal state of the robot. The opposite is the exteroceptive sensors. So those interact with the outside world. So those are, your very classic kind of audio and visual sensors, but there's a few others as well, because there are lots of modes in which, lots of sensors that humans just don't have that we can design hardware to be able to sense instead. So talking about the proprioceptive sensors, the equivalent to proprioception in humans is called an encoder. An encoder is able to measure the rotational position and the speed of a particular joint, or the motor in that joint. You can also have force and torque sensors that can measure the forces that are being applied on the various links as well. Then you have the inertial measurement unit. So for example, I think the Roomba also has one of these as well, which is able to measure essentially the movement of it. So instead of the movement of the joint, it's the movement of the whole body, and in a few different directions. So the accelerometer is measuring the acceleration. The gyroscope is measuring the angular velocity as it's moving through space. And then the magnetometer is quite interesting in that it interacts with the Earth's magnetic fields to actually determine the movement of the body. Okay, and the exteroceptive sensors include, very simply, a camera. You can have black and white, but we tend to go RGB instead. When we say stereo, what I'm saying is that's essentially like two cameras. Now, if you think about how you get depth perception with your eyes, you need to actually have two eyes to be able to have depth perception, because one eye on its own isn't actually able to have that depth to be able to calculate the distance to stuff. And so really, ideally, a robot is able to have stereo vision where when it has two eyes or two cameras to be able to work out depth. Now, a passive infrared sensor, you might have seen images like this before, where it's just measuring the heat. And you can also have GPS, which uses electromagnetic waves that interact with satellites to work out the location of an object. Then all of these types of sensors, so the radio detection and ranging, which is just radar, light detection and ranging, LiDAR, active IR, and ultrasonic sensors, all work in a very similar way. It's kind of like echolocation in a bat. So essentially it's sending off waves, either in the form of radio waves, light waves, infrared waves, or sound waves, and those waves are then interacting with the outside world and bouncing back. And depending on how long it takes to come back, it can calculate the distance that object is away from the body. So the longer the time that it takes for the wave to come back, further away something is. Okay, so my next question, I guess, is what actuators do you know of? And so when I say actuators, what I'm referring to is something that can convert energy into some sort of physical motion. So what in a robot is actually allowing it to move is, I guess, the question I'm getting at. And there's a few different types, but there's one we see really commonly in a lot of things. Any ideas what makes things move? Yeah, motors, exactly. The other ones are a bit trickier. You might have seen them in like machinery, like really heavy machinery and trucks, stuff like that. We'll get onto it. So the most important one is the electrical actuators, or your motors, and these convert electrical energy into motion. There's hydraulic actuators, so those use pressurized fluid. So inside these pistons here is some sort of oil, and it's the movement of that oil that actually allows the movement of the joints. And then pneumatic is actually quite similar to hydraulic, but it uses pressurized gas. And we'll dig into them a bit more. So for electrical actuators, the most simple one is the DC motor. So this uses an electromagnet that allows the motor to essentially spin continuously, really quickly, and it's quite smooth. So you might use this in things like drone propellers. And then the servo motor is a type of DC motor. It has a really high angle precision, so it knows exactly where the joint is placed, because it has a built-in position controller. And so if you remember from before, that's what we call an encoder, right? So it has a built-in encoder into the servo motor, so it knows exactly where it's ended up. While if you take a DC motor, like just a plain old DC motor, the drone doesn't know where the propeller ended up. It's just stopped somewhere. It doesn't know. So this one, it does actually know. And so that's really important to basically have some sort of proprioception. So in robotic arms, for example, we tend to like to use servo motors. Another type is the stepper motor. So the stepper motor has these teeth in here. And so these teeth allow it to essentially take steps as it moves between the teeth. It's kind of like a gear, but instead you have these parts here are magnets that are interacting with each other. And so a typical stepper motor has 200 steps, which when you do 360 on 200, you get about 1.8 degrees per step. And it's relatively fine, and it does have quite precise control, but it doesn't actually have an encoder in it. So the only way it knows its position is just by knowing how many steps it's taken, rather than actually being able to sense where the position is. And so you use this for things that need really high torque as well. So with like a DC motor, for example, once you set it up, it just starts spinning, but this one is able to get to a certain position and just hold that position, and it's harder for it to slip. And so that's what it's these stepper motors that you see in your 3D printer, right? And so to have those 3 degrees of freedom, we have 3 stepper motors that are working in each of those axes. Now, another example is the linear actuator, which is really just another DC motor again, but its movement is being converted into a linear movement. So instead of rotating, it's now moving in and out. And for example, you might have them in a standing desk, so when you press it, it's still a motor that's turning like this, but the actual motion that we see is that the desk just gets raised. All right. Then for hydraulic actuators, as I mentioned, they use a pressurized fluid. So keep in mind that fluid, when I'm saying fluid, it's normally a liquid, so oil, because fluid can also technically include gases. But we're usually talking about liquids. And so liquids are generally less compressible than gases, so keep that in mind. And because of that, because it's not compressible, it's able to really output massive forces and torques. And so that's why they get used in things like heavy machinery and construction vehicles, but they're very maintenance intensive. You can get oil leaks, which can get really messy. And so we don't really see that many hydraulic actuators in robots unless they're doing really heavy lifting. The other one is pneumatic actuators. So these use the movement of pressurized air instead. So air is compressible, of course, and because of that, it can't really work with really high forces, because as you start trying to do, as you try and push stronger things, you end up just compressing the air instead of actually getting the movement that you want. But the good thing about pneumatic actuators is that they're very fast, they're clean. You know, if you get a leak, it's just air. They're quite safe, so you've got no electronics, and they're inexpensive. So they're good in certain situations, but they're not the most ideal in terms of their actual function. And so because of that, they have poor precision, a low force output. They're not overly efficient, again, because of that the compression. So when you put energy into it, it'll compress the air as well as move the end effector. And so one example of pneumatics is in the nail gun. Okay, so now talking through surgical robots. So I guess the reason that we have surgical robots is at least 3 or 4-fold. So first of all, it has surgeon benefits in that it increases precision, it increases dexterity because you can introduce those degrees of freedom, and hopefully it can eliminate tremor as well. It has improved ergonomics for surgeons. So typically a surgeon has to stand up for long surgeries, but for a lot of surgical robots, they end up just sitting on the side with a console. It's much more comfortable. They can churn through a lot more surgeries without getting as fatigued. You also have better visualization as well. And I'm generally comparing to laparoscopic surgeries. Do you guys all know what I mean by laparoscopic surgeries? Like, so essentially where you've got, so for a laparoscopic surgery, there's either open surgery or laparoscopic surgery. For open surgery, you're just opening up, for example, the abdomen, and you can just see everything. For laparoscopic, it's like keyhole surgery. So we cut a few small incisions, and we put in a camera and a few little arms that the surgeon is directly controlling. And they look at essentially a 2D screen. But what surgical robots allow us to do is have a 3D view of what's inside. So without opening up, we can actually have a 3D, we can have depth perception by putting those two cameras inside. There are also patient benefits as well. So you can have smaller incisions, even compared to laparoscopic surgery. And small incisions just mean you're likely to have better outcomes, less risk of infection, faster recovery time. So that's just generally better for patients as well. And in the future, we have the potential for telesurgery, where you don't even have to have a surgeon in the room. So you can have the robot in one place, the console somewhere else, and the surgeon can then perform those surgeries. And possibly we could even get to automation, where there is no surgeon involved whatsoever, unless for a backup. So talking through some of the surgical systems, so we'll talk briefly about the Da Vinci, but we'll come back to it later. It is definitely the most widely used surgical robot, and I think it got FDA approval in 2000. And yeah, this is the one that's primarily used for laparoscopic surgeries, generally in general surgery, urology, and gynecology. It's what we call a master-slave system. So master-slave in that the robot, it doesn't really have any autonomy whatsoever. It is the surgeon that is telling the robot what to do through the console, and the robot will just act accordingly. The next one is the Mako Smart Robotics system, which is used for orthopedic surgery, so primarily knee and hip replacements. And so this is a semi-active type of surgery. So instead of the surgeon controlling it, you actually have this robot here, and the surgeon's actually at the patient bedside as well. And what the robot is doing is that it's guiding the surgeon as to where to put their instruments. For example, if they're shaving down part of the inside of the knee joint because they're going to put a knee replacement in, it'll make sure that they cut to the right depth. It'll make sure that they're not doing anything dangerous. And so it just limits the surgeon's movements a bit and guides them a bit. So it's considered semi-active rather than the surgeon making all of those decisions themselves. And so before we do those surgeries, they do a CT-based 3D scan. And so the robot is always looking at the scan as you're going through the surgery as well. The Rosa One brain is actually quite similar. So it also uses a semi-active system, except this one is used for neurosurgery. And so you can imagine neurosurgery is a very fine and precise skill to have because you're working with the brain, of course. And what this looks like is, again, you've got a robot here that is guiding the surgeon as to where exactly to place their probe or whatever instrument they're using. And again, it uses imaging to be able to guide the surgeon to exactly where they need to place their instruments. So yeah, it allows for very, very high precision. All right, so the Monarch platform is not actually really surgical. It's more of a procedural one that they use for diagnostics, and it's currently used for bronchoscopy. So it is a catheter, so it's like a tube that goes in through the mouth, through the trachea, into the lungs, and can be used for taking samples of the lungs, like biopsies, to check for cancer, for example. Now, this one is, again, a master-slave system. So the surgeon is not at the bedside, they're at their own console, and they're telling the robot exactly where to go. But you can imagine that something like this might be able to be used for something like a colonoscopy or gastroscopy again. So I'm sure that's something that people are working on as well. And the last one, CyberKnife, is not actually surgery, because we're actually doing radiotherapy with it. But it is able to provide really precise radiotherapy. And it's definitely the most autonomous of the systems that we've talked about so far. Because the way that this one works is that the radio-oncologist sets up the procedure. They define what is the target and where in the patient that is, and gives the machine a patient. But then once it's started, this arm is able to move around in different directions, is able to adjust the patient accordingly, adjust for the breathing of the patient, and is able to apply high doses of radiation really precisely. And one of the really beneficial things for the patient especially is that it is frameless. So if you guys have ever seen people who need radiotherapy, they often need to get strapped down essentially, which is quite limiting for the patient, quite difficult. And so they don't need this because the robot is able to automatically adjust for that. So it can apply much higher doses of radiation because it's very precise. And so you can do them in 1 to 5 sessions rather than 20 to 40 sessions, which you might typically need for a set of radiotherapy. So, some of the limitations of surgical robots is that number one is that they're very, very, very expensive. So the newest Da Vinci robot runs at about 4 million Australian dollars. So you can imagine, like a lot of big hospitals might only have one of these robots. So it's quite prohibitive for now, but there are a lot of other companies that are working on making surgical robots as well. And so as we start seeing more surgical robots enter the market, I'm sure we'll see a decrease in the price of those robots. And I'm sure that will also result in less bulky hardware because they are quite large at the moment and made up of multiple components. It is, of course, also a new thing for the surgeons to learn because they all learn their techniques to do open surgery, to do laparoscopic surgery. Doing this is a completely new ballgame. Yes, you're achieving the same things, but you now need to know how to use these controllers as well to achieve the same outcomes or even better outcomes, hopefully. Now, regulation is always going to be a tricky thing as well because essentially as we create new robots, often there is no current regulation for these new technologies. And so because they can't get approved because there's no regulation in the first place, it takes a while for those robots to get that approval and to get used in hospitals. Another thing is that because they're so expensive, there is limited access in low resource settings. So you'd expect that these robots are obviously going to end up at the richer hospitals. Like for example, I know the Alfred has one. So yeah, it's going to be a much slower rollout to the lower resource settings. So going into a bit more about the Da Vinci Surgical System. So as we mentioned, it has a surgeon console. So this allows the surgeon to essentially feel like they're inside the patient because they have the two cameras that go inside and give them that 3D vision. And so it's like they've stuck their head inside the patient without actually opening the patient up like they do for an open surgery. Now it has two hand controls for each of their hands, and it also has foot pedals, and the foot pedals help them switch between the different arms that it uses and between using different tools for each of the arms as well. So I mentioned the vision system already, which is the set of cameras that it has. So it allows for a 10 times magnification of the inside as well. So for the arms, one arm is dedicated to having the two cameras, and then it can have 2 or 3 arms depending on what setup you have, depending on the generation of the robot that you have. And these all work with an endo wrist, and this is where the degrees of freedom come into it. So the endo wrist, which is all inside the patient, has on its own 7 degrees of freedom. So there's a lot of dexterity inside the patient as well. So it's kind of like you're able to do open surgery without actually opening the patient up, because you have just as much dexterity as you would with your hands inside the patient now with those robotic arms. And so you can imagine the sensors that you would need inside this robot is, of course, it's going to need encoders because it needs to know where each of the components of the robot are situated. It needs to have force and torque sensors so that it can measure the loads that it's carrying and for safety reasons as well. And the actuators are actually DC motors, and they call them DC motors at maximum, but they're really just like servo motors, because again, servo motors have to have those encoders so they can have really precise measurement of where the arms are located. And then again, when we put that all together, we come back to kinematics. So the robot is able to use inverse kinematics to calculate what joint angles it wants to use to be able to get the tip of the arm at the right location. And then using forward kinematics, it can do the reverse and then double check where the end of the robot is. And so using these two together and a few other processes, it can do motion scaling. So motion scaling is where, say you move your hand by 5 centimeters, it can scale that down to only a 5 millimeter change inside the robot, inside the human body. It also filters for tremors as well. So I guess one thing I was considering is, so the Da Vinci robot is a master-slave system. So does it really count as a robot if it doesn't have any of that autonomy? So I guess considering the core criteria for it, is it able to interact with the physical world? Yes. Does it have sensors? Of course. Does it compute? Yes. It filters the tremors, it scales motion. It also has safety limits, so even if a surgeon is trying to push too far one way, it'll just stop eventually at one point due to safety. And it has motors. So I guess the only question is, does it really have autonomy? And I guess big picture, no, but it does have some autonomy in the fact that it is able to adjust the surgeon's movements in particular ways. It is programmed to be able to do that. So it's a bit ambiguous, but I would say yes, it does still fit under the definition of a robot. So, for the future of surgical robots, do we have any thoughts as to what we could do to improve surgical robots, or what else we'd expect to see in the future? And I might have mentioned some of these things already. Yeah, exactly. So automation, for sure, we have. I guess another thing to think about is, so when a human does an open surgery, what of our 5 senses are they using to perform their surgeries? The primary one is sight, of course. Touch, exactly. So at the moment, yes, the robots can feel some form of force being applied as they're pressing on certain things, but the surgeon can't feel that. And so that's something we'll talk about, which is called haptic feedback. Any other ideas? All right. So, yeah, the first one we wanted to talk about was haptic feedback. So that uses the vibrations, and then other movements of essentially the console to be able to relay feelings inside the human. And so we use like really basic haptic feedback for other things. So if you've ever played certain games on your Xbox, if you're playing a shooting game, right, and you get that recoil, you start feeling the controller buzzing, right? And that's supposed to give you some sort of almost realistic feeling of being in that situation, what it would actually feel like. And so when we extrapolate that to surgery, we want to be able to essentially feel what the insides of this person is without having to open them up, because that's not something you can do laparoscopically, it's only something you can do with open surgery. And so the goal of having haptic feedback is to give surgeons that sense of touch. It also increases their precision as well, because they know exactly what they're touching. And yeah, currently there's no tactile feedback, but the sensors you require for that are essentially force, torque, tension as well, feeling the tension in various pieces inside the body, as well as tactile feedback as well. And you have to have really miniaturized motors to be able to relay such fine detail as well. And this is technology that I guess we are working towards having, but we haven't put together quite yet. Another one is remote surgery. So one of the things I mentioned before, so at the moment, the surgeon still sits in the same room and performs the surgery. But what if you could have, the surgeons sitting somewhere in Melbourne in one big hospital like the Alfred, but then you have a robot out in Traralgon, for example. So that reduces your need to have those surgeons in those areas. So in theory, it can increase geographical access to certain procedures. Now, I of course have to bear in mind that these robots are super expensive, of course, but in theory, if you're able to have enough of these robots, you don't actually need your surgeons spread out in all these places. You don't need to keep flying people out from really remote areas, because if you have one of these robots there, they can perform the surgery there. And so I guess one of the difficulties with that is, yes, we already have the console, we already have the robotic arms, but we also need to be able to relay that information quickly from wherever the surgery is being performed to where the surgeon actually is. And so we have to have lower latency and higher bandwidth networks. So latency being like essentially the lag in the system in the message moving through the system. Bandwidth kind of referring to how much data you can move. And so if you have, we have 5G right now, but if we move towards 6G and 7G, etc., we can increase the speed of that information being transferred. And so hopefully you can have, when the surgeon moves, the robot moves almost instantly. It would be great to have haptic feedback as well, because again, that increases the precision and the safety of surgeries. And ideally, well, what happens if you've got one person in Mildura, one person in Clayton, and you lose connection? someone's got to do something about it, right? Now, if you don't have the surgeon there, there is no one that can possibly fix that. And so at least earlier on, you might want to have autonomous backups for that, so that the arms are at least safe, can finish, even if you can't finish the surgery, it can at least retract the arms or stop any bleeding before it does that. So some sort of backup protocol that will prevent any further harm happening. Because obviously it is quite dangerous when you don't have a surgeon in the room, but you have surgery being done. Another interesting one is micro-robotics. So this is essentially talking about robotics at the micro level, so the micrometers, sorry. And so these can be used to reach really difficult to access places. They can be used for drug delivery, for biopsies of hard to access places. Again, because not all probes can reach really small parts. Like one example is that we take that robot that can do bronchoscopy, right? It can only take samples of, for example, what we might think is a cancer from the larger airways. It can't reach all the way into the alveoli. And so if you want to really biopsy something in its earliest stage, you want to have something that's really small that can reach it. And so that's where micro-robotics might come into it as well. And so you can imagine, you can also have stuff like a steerable capsule that can do endoscopy for you as well, or gastroscopy. So the challenges with that is that, first of all, the physical properties, so the way that physics works at a micro scale is just different. So there's so many other challenges that you run into, even at the micro scale. And the fabrication of really small sensors and actuators is something that we just haven't been able to do yet. And I guess another thing that we can get into is soft robotics could be used, especially for navigating really narrow anatomies. Now, the final topic I wanted to talk about was physical AI, so automating surgery. So what is physical AI? Physical AI is essentially when robotics meets AI. Now, at the moment, it can do things like putting stuff away in the fridge. So we're way away from being able to have completely autonomous surgery. But the goals of it is that ideally, it doesn't have to necessarily replace the surgeon either. It can just be a smarter surgical assistant, right? And so it can, instead of replacing the surgeon, it could augment the surgeon's performance instead. It can also replace certain really repetitive tasks that the surgeon might need to do, like suturing, for example. So the surgeon can do the complicated part of actually, say, resecting a tumor, and then when closing up, the robot can just be automated to quickly go through and put through all the sutures and tie them up. And I guess at the very, very end of physical AI would be autonomous surgery where there is no surgeon involved whatsoever. So the technology that needs to be developed to get there is we need to have computer vision and multimodal sensors. Now, I guess one of the interesting things with robots, again, is that they can sense so many things that humans can't sense. And so what if we could introduce new types of sensors that, because before I'm thinking about haptics, I'm thinking about vision, because that's what humans can do. But what if there's other things that robots could measure inside a human that would be more useful, that would give us new insight and lead to better surgeries as well? We then, of course, need an intelligence layer that's going to process all this information. So you're going to have multiple modules in your AI. So you're going to have a perception module, which is going to take in all this sensor information, reasoning, which is going to decide what to do next, control, which is going to control what the robot will actually do, and then language as well, because you need to be able to process whatever instructions someone gives through language to the robot for it to then be able to perform that. And then finally, for the action layer, again, we're just talking about having really precise actuators and ideally miniaturized end effectors. And so I guess, what are some other considerations that we have to think about if we wanted to automate surgery? And think broadly, don't think about just technology. What about like ethics or legality, anything else? Any other considerations? For sure, exactly, liability. So who would be responsible if there's an autonomous robot that is doing surgery? If something goes wrong, is it the surgeon that is supposed to be supervising the robot that is liable? Is it the company that made the hardware for this robot? Is it the company that maybe it was another company that made the actual software for this robot? So then who's actually liable for it? So that's definitely a question that we'll have to be able to answer at some point. Any other considerations? Yeah, exactly. Regulatory lag is always going to be an issue. Well, I guess, would you guys want a robotic, like an automated robotic surgery robot to do a surgery on you or your family? Not the first one, right? So there's definitely going to be a lot of new perspectives from patients and surgeons. Like, people may not want this, for example. Surgeons especially might be resistive because they're going to lose their jobs hypothetically. Patients may not be trusting it initially. So there's a lot of considerations with that as well. Anything else? Privacy for sure, yeah. So, because you're running all of these images through a model that is, well, hopefully hosted locally in the hospital, but if it's sent off to the cloud, yeah, you definitely have to think about that. I feel like even for like remote surgery, what if someone else is able to hack into the feed that's going through? Yes, privacy is an issue, but what if they can also control the arms, for example? So I guess, yeah, a few things. So when we're thinking about the AI specifically, in terms of training a model to be able to do to be able to do robotic surgery, like, where does the data come from to be actually train a model like that? Like, yes, you can train on visual data, of course, like videos of surgeries, but then what about all the other sensors that you want to input, right? Like, how are you going to train a robot to be able to have tactile feedback if we don't have any sensors that are able to currently give the robot tactile feedback, right? And so one interesting idea is, and that they're using for physical AI already, is using a simulated environment so that it's able to replicate the physics of the real world. And so when this robot, so the robot almost thinks that it's in the real world, but it's not actually, and it's still getting that sensory feedback without actually risking, the safety of the patient. The other thing I guess I'm thinking of is some of these robots may just have to essentially assist in a bunch of surgeries, and over time they will learn how to do them as well. Another thing is benchmarking. So how do we grade the performance of a surgical robot? How do we compare it to humans? Is something to think about. Another one is interpretability. So, AI is a lot of it, like especially new AI, is like really like a black box. You don't really understand often what is going on inside, why it makes those decisions that it does. And that's something that ideally we need to be able to understand to be able to so that we can actually know why it has gone down making certain decisions. Another thing, of course, is safety. So that's always going to be an issue. And I feel like they probably need some sort of human override system as well, in which, if something's going wrong, the human can just turn off the automated side of it and just take over. And so it needs some sort of backup there. We already talked about regulatory hurdles and liability, the ethics of using AI robot, and yeah, social acceptability as well. And I guess my final question for you guys is, and something to discuss for us as well, is what do you think the final form of an automated surgical robot would look like? So do you think it would be more like something like this, where it's humanoid, where it's meant to look like a human, or do you think it'll be more like robotic arms? Robotic arms? Yep. Do you think in the long term we'll move towards humanoid like surgeons?
I don't think humanoid will be more effective. I think there's also more risk factors.
Yep. Any other thoughts? Do you guys agree? Yeah, I think so too. Because look, one way to think about it, like, when we talk about like automating, for example, the work that doctors do, you could have a robot that can do what a doctor do. It can examine a patient, it can take a history, examine a patient, then do a surgery on it, right? But do you really want that robot to be able to do all those things? Or would you rather you have a robot that can examine a patient and then a robot that can do the surgery? Like, does it need to be able to have all of those capabilities? Because I feel like that would probably just make it unnecessarily expensive. Exactly, and it's so much more complicated Well, if you can specialize these robots in tasks that are relatively general, still like ideally, I feel like, surgical robots would eventually get to a point where they can do a wide range of surgeries, but I feel like they probably don't need to do all these other things. So yeah, I'll leave you with that thought. Did you guys have any questions before we finished up? No? All right, well, thank you all for your time. Please scan the QR code to give us your feedback. Thanks, guys.